Hi everyone, I'm Christina and welcome to the fourth video in our A-level trigonometry series. In this video, we're going to look at proving trigonometric identities. So we've learnt a range of trigonometric identities from previous videos, and I've made a note of them here in purple because we're going to reference them in some of our worked examples. But in this video, we're going to focus on how to actually use these identities to prove that two expressions are equivalent. So let's go through some of the objectives in this video. So our first is to recognize when to use a known trig identity to manipulate and simplify an expression, and then work through a show that identity and transform one side into the other. So typically, the way we work with proving trigonometric identities is we work on the left-hand side and try to find a way of manipulating the expression on the left so that we can show that it's equivalent to the right-hand side. We do not try to manipulate both sides at the same time. You work firstly on the left and try to get to what you have on the right. And from there, we also want to introduce this equivalence notation that I've just written down, which is 3 horizontal lines, which is different to your equal sign, your usual 2 horizontal lines. And it needs to be emphasized that we are not solving an equation here. We are showing that the left-hand side is equivalent to the right-hand side for all values of x or theta, where both sides are defined, which is why we're introducing this equivalence notation when we're proving identities, as opposed to just solving equations, which for that we can stick to our equal sign. Okay, so let's look at our first example and work through it together. So we want to show that sine squared theta brackets sec squared theta plus cosec squared theta is equivalent to sec squared theta. So again, what we're doing here is we're going to start on our left-hand side, and we're going from the left-hand side to the right-hand side. So we want to show that this expression that we have on the left is equivalent to sec squared theta. So the first thing we're going to do is expand the brackets on the left. So let's do that here. I can write that as sine squared theta, sec squared theta, plus sine squared theta, cosec squared theta. Now, sec squared theta is just 1 over cos squared theta, and cosec squared theta is 1 over sine squared theta. So you can look back to previous videos to see that. So we're writing down our reciprocal functions. So sine squared theta over cos squared theta plus sine squared theta over sine squared theta. So from here, sine squared theta over cos squared theta, well, sine theta over cos theta is tan theta. So then that first term is just tan squared theta. And then our second term, sine squared theta over sine squared theta, is just 1. And now we can look up here to one of our identities that we looked at in the first video, sine squared theta or sine squared x plus cos squared x equals 1. Well, we know that we can transform that a little bit, and I'll just write it out here. Sine squared x plus cos squared x equals 1. If we divide each term by cos squared x, we get tan squared x plus 1 is equal to 1 over cos squared x, but that's just sec squared x. So I'll just write that here. Sec squared x there. So we can see tan squared theta plus 1 is just sec squared theta. So in fact, we've proven this trigonometric identity here. We've shown that the left-hand side does in fact give us the right-hand side. Okay, so let's move on to our second example here. What we want to do is show that sine of 3 theta is equivalent to 3 sine theta minus 4 sine cubed theta. So again, what we're doing is working from the left-hand side, and we're trying to get to the right-hand side and show that they're equivalent. So for this one, we can rewrite sine 3 theta as sine of 2 theta plus theta. Now, why is this helpful? Because if we look back to our previous identities, we can then use our compound angle formula for sine. So we can use sine of a plus b, where a is theta and b is 2 theta. Or we can do it the other way around, where b is 2 theta and a is theta. And we can then write sine of 2 theta cos of theta plus cos of 2 theta sine of theta. Okay? So let's do that here. So now we're applying our compound angle formula for sine. So we're going to write sine of 2 theta cos theta plus cos of 2 theta sine of theta. But here we can see that we actually get our double angle expressions, the sine of 2 theta and cos of 2 theta. So we can rewrite that again, and we can have a look up here to see which ones we might want to use. So sine of 2x is just 2 sine x cos x. Cos of 2x has a few forms. So let's look at which one would be most appropriate to use here. So we can write sine of 2 theta as 2 sine theta cos theta times cos theta, and then plus, okay, cos 2 theta sine theta. Well, we can see that in our example here, we have sine cube theta and sine theta on the right-hand side. So that tells me that it might be most useful to use the form of cos 2 theta where we have our sine function. Our sine function only, as the right-hand side here doesn't have a cos function. So then what I'll place here is 1 minus 2 sine squared theta. So this is the form of cos 2 theta that we're going to use. And it's okay sometimes to not know for sure which one you use. You are just trying to manipulate the expression to see what comes out of it. And you might make mistakes at first, but it gets easier as you do more. So now we can expand everything here and simplify a little bit. So we can write 2 sine theta cos squared theta plus sine theta minus 2 sine cube theta. Okay, and we know from before cos squared theta, we can again use our sine squared x plus cos squared x equals 1. So we can rewrite that in terms of sine, 1 minus sine squared theta plus sine theta minus 2 sine cube theta. And I'll just continue here, 2 sine theta minus 2 sine cubed theta plus sine theta minus 2 sine cubed theta. So we're almost there. And that is just equal, okay, collecting like terms, we get 3 sine theta minus 4 sine cubed theta. So here we can see that sine 3 theta is in fact equivalent to 3 sine theta minus 4 sine cubed theta, because we start on the left-hand side, we rewrite sine of 3 theta into sine of 2 theta plus theta. We substitute those in for a and b in our compound angle formula for sine, and we do in fact end up with what this expression has on the right-hand side, which is 3 sine theta minus 4 sine cubed theta. Okay, so those are our 2 worked examples, and hopefully it's clearer to you how we approach proving trigonometric identities.